Hello AP Calculus students. So this is actually the third time that I've tried to make this video. The first time my app decided to not save it. The second time I guess I just forgot to press the button. So definitely a little bit of frustration here, but hopefully this third time is the charm. So this is actually the beginning of a new unit, our second to last unit of the AP Calculus curriculum. It's not a very long unit. We'll finish it up in a couple weeks, honestly. And it should be easier than the previous unit, which I know some of you found a little bit tricky. But before we get to it, let's try out this bell ringer. So if f is differentiable, we can use the line tangent to f at x equals a to approximate values of f near x equals a. Suppose this method always underestimates the correct values. If so, then at x equals a, f must be blank. So let's try to highlight some keywords here in this question. And hopefully you've tried this problem out yourself first before going over it with me. So some keywords. So it talks about approximating a function value using a tangent line. So that is definitely a topic that hopefully you should have heard of previously. Using tangent lines to approximate the value of a function is a topic that we have covered. It's where we always find the tangent line equation first, and then we simply plug in the x value into the tangent line equation to approximate the given function. Now we're told that this tangent line approximation always gives us an underestimate. So in other words, it's telling us that the tangent line always gives us an answer less than what the actual function value is. So let's go through these choices and see if we can figure out which one of these always guarantees an underestimate. So this first choice, positive. So if f is positive, that just means it's above the x-axis, Well, if a function is above the x-axis, we can draw one out really quickly. If a function is above the x-axis, it could look something as simple as that, as a straight line. Now, if I were to draw the tangent line equation to this straight line, you would see that it is actually on top of the original function graph. So the blue line is the tangent line equation, and that it is actually on top of the orange original function. Now, at this point, this can give us an underestimate. If the line is on top of each other, that means the tangent line is going to give us the exact value of the original function. So that's not going to work. That's not going to give us an underestimate. So now the next choice tells us increasing. Well, let's see what an increasing graph looks like. An increasing graph can look something as simple as a straight line that's always going up. Well, if I were to draw a tangent line to this graph, once again we run into the same issue where we have a tangent line that is right on top of the original function graph. So the tangent line is blue, the original function graph is red. So once again, that is not going to give us an underestimate because the tangent line is going to have the exact same values as the original function graph. So that one's out as well. And the same thing happens with the decreasing the decreasing graph as well. If you draw a decreasing graph, the line is just going to be going down, but the tangent line is once again going to be right on top of it. So it's just going to give us the exact same values. So the decreasing is out as well. So now let's look at concave upward. Now we've talked about in class this idea of concave upward. When you visualize a graph that's concave upward, you want to visualize a parabola, an upwards facing parabola. So let's draw an upwards facing parabola on this graph. So that's an upwards facing parabola. So that graph is concave upward. So now let's choose a point and draw a tangent line to that point. So let's just choose a point. So we'll choose that point. Let's zoom into here. And let's draw a tangent line to that point. So if we draw a tangent line to that point, you'd probably get something like this. It might not be exactly like that, but approximately it will be something like that. So now let's choose another x value. So let's just choose, let's say this x value. We'll call it b. Okay, so right around here and here. So that is where both of those graphs would be at that respective x value. Well, if we call the orange graph f, so f of b is going to give us some y value. And if we call the blue one g of b, that's also going to give us some y value. Now, I hope you would agree that by looking at this graph, you would see that f of b is going to be greater than g of b, right? So f of b is going to be greater than g of b because the y value is higher, right? The y value is higher than where the green point is on the blue line. So what does that mean? Well, it means that the tangent line is always going to give us an underestimate. The tangent line is always going to give us an underestimate because no matter what x value I'm going to pick, the line is always going to be lower than where the function curve is. The function curve is always going to be higher than where the tangent line is, since the original function graph is concave upward. So that is going to be an answer for this question. That is going to give us the underestimate in all situations. If you try the concave downward choice, you would just draw an upside down parabola, and you would see that the tangent line is always higher. It's always going to be higher than the original function graph. So that's our bell ringers, just a little bit of review of tangent line approximation. A good conceptual question, not much math to it, just being able to draw what each of these graphs would look like. So let's get to our unit. So unit 7, second to last unit. So the title of this unit is called Differential Equations. Now, right off the bat, I will say that this is a very popular topic when it comes to the free response section of the AP Calculus exam. At this point, I would even call it as being a near guarantee that you will see a free response question dealing with this unit. So I would definitely encourage you to master it to make sure you can get some good points out of that section of the exam. So let's get to this idea of what a differential equation is first. So a differential equation. Oftentimes, physical phenomena can be described by a differential equation or an equation involving a derivative. So that's the key word here. A differential equation is an equation that has somewhere in it a term that is a derivative term. So it could be the first derivative, it could be the second derivative, as long as it has some kind of term that is a derivative. Now, up to this point, we've seen many differential equations, actually. Back in semester 1, whenever we were asked to find the derivative of a function, you found a differential equation because that resulting equation always had a derivative term in it. So as long as your equation has a derivative, as long as one of its terms is a derivative, it means it is a differential equation. Now, throughout this unit, you'll see a lot of application or contextual questions dealing with differential equations. So things such as radioactive decay, population growth, Newton's law of cooling, all of those are going to be involving differential equations. And as a result, since they all have derivatives involved in them, that means they will involve rates of change, okay? Remember, derivatives are just rates of change. We actually did a few lessons before this, a problem where we looked at the rate of change of the population of coronavirus. It was originally bacteria, but we changed it to coronavirus to make it a little bit more applicable to to the goings-on in real life. So that would have been an example of a differential equation. Let's get to the first type of problem that you can see, and the first differential equation for this lesson. So determine whether the given function is a solution of the differential equation y double prime minus y is equal to 0. So this right here is a differential equation. Why? Because of this y double prime term. Remember, y double prime is just the second derivative of y. So since that term is there, that makes this equation a differential equation. So we're asked to determine whether each of these three given functions is a solution to this differential equation. So what does that mean? It means that if we were to take each of these functions and plug them in appropriately into the differential equation, does it make the equation true? So this first equation, we have y equals sine of x. Well, we know what y is equal to, but we don't know what y double prime is equal to. But let's find what y double prime is equal to. Well, to find y double prime, we need to know what y prime is equal to first. So y prime is just the derivative. So the derivative of sine of x is just cosine of x. And then y double prime is just the derivative of that derivative. So the derivative of cosine of x. So negative sine of x. So at this point, all we're doing is we're taking that differential equation, so y double prime, minus y is equal to 0. And we're going to take each of these and substitute them in. So sine of x, we're going to substitute it in for y. And negative sine of x, we're going to substitute it in for y double prime. Now, we're not going to substitute in cosine of x because there is no y prime in this differential equation. So once we make those substitutions, we end up with negative sine of x minus sine of x equals 0. Or question mark equals 0. We're trying to determine if it does equal to 0. Well, we have negative sine minus sine. Those do not cancel out because one of them is sine. So you end up with negative 2 sine of x, which I hope you agree does not equal to 0. So this is not a solution. Okay, it is not a solution because when we substituted in, it did not equal to 0, which is what this equation is equal to. So it is not a solution. So once again, not very difficult. You just got to make sure you find the appropriate derivatives and then just plug in accordingly. So now let's look at B, the next equation that we're given. Y equals 4e to the negative x. So once again, we're going to do the same thing. We're going to find y double prime, but to do that, we have to find y prime. So always recall that the derivative of the e function is just itself, so 4e to the negative x. Now we do have to multiply by the derivative of the inside, so we do have to use the chain rule, people. So our inside function would be the exponent. So since our exponent is negative 1, we will be multiplying, since our exponent is negative x, the derivative of that is negative 1. So we're going to be multiplying by negative 1. So this is just the same thing as negative 4e to the negative x. Now let's do the double derivative, negative 4e to the negative x. We have to use the chain rule again. Once again, multiply by the derivative of the exponent. Our exponent is once again negative x, so we will be multiplying by negative 1. So this simplifies to positive 4e to the negative x since the negatives just cancel out. So we have y double prime minus y is equal to 0. So y double prime is just 4e to the negative x, and y is just 4e to the negative x as well. Does this equal to 0? Well, if you subtract the term by itself, you should get 0, so that works. So this is a solution. So this y equals equation is a solution to this differential equation. So that's what it would look like if it was a solution. The left side has to be equal to the right side. So the left side was equal to 0, right side is equal to 0. Boom, it's a solution. Now let's finally look at C. So this one is similar to B. So that capital C just represents a constant. It's not a variable, it's just a constant. So let's find our y double prime and our y. I'm just making sure that I'm recording. I don't want to make the same mistake that I made last time. So y prime is just going to be c e to the x. Now at this point you might be saying, let's do some chain rule, which you can. But you'll notice our exponent is x this time. So the chain rule would tell us to just multiply by the derivative of x. The derivative of x is just 1, so you can multiply this by 1, but it would just end up being the same thing. And then y double prime just ends up being the exact same thing. Capital C e to the x. So y double prime minus y, does it equal to 0? Well, y double prime is c e to the x. Y is c e to the x. Does that equal to 0? Once again, we have a term, or we have a term subtracting by itself, so that does indeed equal 0. So is a solution. So that works as well. So two of these three functions were solutions to these differential equations. So not very tricky. You got to be able to know how to find a derivative. At that point, you just plug in the appropriate terms and you verify whether it makes the equation true. If it makes the equation true, it's a solution. If it does not, it is not a solution. This is a type of question you can probably see as a multiple choice question where they give you choices which one of these equations is a solution, and then you just have to test out from there. So let's look at the next major topic of this unit, which is this idea of slope fields. So what is a slope field? So a slope field is basically a grid like the one you see before you, and you'll see in each of these points that are already plotted on this grid, we are actually going to find the slope at each of these points, and then we're going to plot those slopes using like these mini lines on this grid, hence the name slope field. So once we're done with this grid is going to be filled with a bunch of mini lines that represent the slopes at each of these points. Well, how do we find the slope? Well, so we're given a differential equation, dy dx, which, remember, is just is one of the many notations we use to represent the derivative of an equation. So that's the derivative. Now remember, derivative is just a fancy word for slope. Just a fancy word for slope. So this gives us the slope of our function at every point. So we're going to be using this equation to find the slope at each point. So we're going to do a few together. So for example, if we did 1, 1, so remember, 1 is our x value, 1 is our y value. So 1 goes for x, 1 goes for y. So we get negative 1/2. So our slope at 1, 1 is negative 1/2. Excuse me. So we're going to draw a mini line at 1, 1. And what I mean by a mini line, so first we're going to draw a line with a slope of negative 1/2 at 1, 1. So a slope of negative 1/2, so it's probably going to be something like this. So there you go. So once again, just a mini line segment basically at 1, 1 with a slope of negative 1/2. So the slope is negative, so that's why the line is going downwards. Slope is negative. And then since it's 1/2, it's not going to be perfectly diagonal. It's not a slope of 1, so it's going to be slightly flatter. You'll see there isn't an exact science to this idea of slope fields. Like, it's really hard to draw a slope that's exactly 1/2 on this. So there is going to be a margin of error for some of these. I will make a comment later in this problem just as an overview of exactly what the AP graders are expecting to see in a problem like this. So we'll revisit that. So let's do a few more points. We did 1, 1. Let's also do negative 1. Whoops. Let's also do, okay, we're still recording, good. Let's also do negative 1, 1. So negative 1, 1, if we do negative 1, 1, so negative 1 is the x value. So negative 1, negative 1. 1 is the y value, so 2 times 1. The negatives cancel out, so 1 over 2. So now we have positive 1/2. We have positive 1/2. So positive 1/2 is going to be just as steep as our initial point. It's just going to be in the positive direction, so it's going to be going upwards. So at negative 1, 1, we're probably going to have a slope that looks something like that. So something like that. That's going to be the slope at negative 1, 1. So once again, positive direction this time since the negatives canceled out. Okay, so that's what you would do actually for each of these points in a problem like this. You would plug in the appropriate x and y values and then just draw the appropriate slope from there. So now let's do the next one we're going to do. Let's do 0, 1. So 0 for x, 1 for y. So 0 for x, 1 for y. So that's just 0 over 2, which is 0. Now, remember, a slope of 0, which is what we have here, a slope of 0 is a flat horizontal line. So at 0, 1, we are going to have a flat horizontal line. All right, so something like that. And for good measure, let's do these next three actually also end up being 0. So 0, 2, 0, negative 1, 0, negative 2. Those are all 0 because the x value ends up being 0. And if you plug in 0 in for x, it makes your whole fraction equal to 0. So the slopes at those are 0 as well. So that, whoops, sorry again, apologize. Let me get that back. Okay. So you get 0 here, 0 here, 0 here. Now you'll notice I skipped the origin. So I skipped 0, 0, and there's a reason why. If we do 0, 0, so let me do 0, 0 on the side here. If we plug in 0, 0, we end up with 0 for x and 0 for y. Now, remember, going back to when we did a lesson on L'Hopital's rule, this is not equal to 0. It could be equal to 0. It's not a guarantee, though. It could be equal to 0. It could be equal to 1. It could be equal to 2. Without more information, we cannot determine exactly what 0 over 0 means. So for that reason, we do not draw anything at 0, 0 because dy dx goes to 0 over 0 at that point. So don't draw anything at 0, 0. And the same rule actually applies for these next 4 points. So 1, comma 0, 2, comma 0, negative 1, comma 0, negative 2, comma 0. For each of these, you'll notice that the y value is 0. And if our y value is 0, the denominator is equal to 0. So for 1, comma 0, you end up with 1 over 0, 2 over 0, negative, negative, 1 over 0, 2 over 0. Remember, when you divide by 0, that is undefined when you divide by 0. It is undefined, okay? So as a result, we're not going to plot anything there either. Now, some of you might make the argument, well, didn't we learn that if it was an undefined slope, that means it was a vertical slope? Yes, we did learn that. The only problem is that's not the only situation where you have an undefined slope. It's possible it's vertical there. It's possible that the tangent line is vertical at those points. But once again, without more information, we cannot be sure. Because other situations in which you will have an undefined slope are, for example, when you have holes. So in other words, when your function is not defined at those values. Or another situation is where you have those asymptotes, where the curve just gets closer and closer to that value, but never actually touches it. So we don't know which one of those 3 situations we're in, so hence we are not going to draw anything along these 5 points, all right? So these 5 points are along the x-axis. We are not going to draw anything there because without more information from the problem, we don't know exactly what's going on there. Now, I think I'm going to do 2 more together, and then I'm going to speed through the rest. So, for example, if we did, 2 comma 1. If we do 2 comma 1, so 2 for x, 1 for y, you end up with 2 for x, 1 for y, so you end up with negative 2 over 2, which is negative 1. So our slope is still negative, except this time it's 1. So as a result, the line that you should draw at 1 comma 2 should be steeper than the line that you drew at 1 comma 1, because remember at 1 comma 1 the slope was 1/2, the slope at 1 comma 2 was 1. 1 is going to be a steeper slope than 1/2, so this slope has to be steeper than this slope. Those are the kinds of things they would look for on the AP exam. In other words, they're looking for consistency in terms of, is the slope negative here? It is negative here. Is the slope steeper here than at this point? It is. Those are the kinds of things that they're going to be looking at. So that's the kind of margin of error you're going to have. So that's where you got to be consistent. And then the last one I'm going to do is 1 comma 2. 1 comma 2. So 1 comma 2. So 1 is for x, 2 is for y. So 1 is for x, 2 is for y. So this gives me negative 1/4. So negative 1/4 now still negative, but even less. It's even less steeper than 1 comma 1. So it's going to look something like, if I get this right. So it's going to be even flatter. So it's probably going to be something like that. Okay, so something like that. So once again, just to recap, 1 comma 1 was 1/2. 2 comma 1 was 1. So this had to be steeper than this one. 1 comma 2, 1 comma 2 is 1/4. So this had to be flatter than this one since this one was 1/2. Now the rest of these points I'm just going to speed through. Sorry. I'm just going to speed through, so you can fast forward, or if you want to try them out yourself, you can do that too. So let's see. So this should be 1. This should be negative 1. This should be, almost did it. Oh, no, I was right. So this also should be positive 1. All right, so we got those. So let's see what else we got. We have some 1/4. Some 1/2. So this is probably around here. And then we have another one like here. Okay. Almost done. So then we have the 1/8. The 1/4. So right around here. So it's going to be pretty flat. And we have another one here. Okay. Whoops. Messed that one up. Should be negative. Drew it as a positive slope, so that's a good Okay, there we go. We got that. And then we got this one over here. We want it flatter. Okay. And then the corners, which should be 1/2. So there's going to be something like this. So we got that. And over here. Oh, made another mistake here. It's okay. I'll fix it. Got that one. Got that one. I made a mistake right here, if you notice. This, oops, sorry. Oh, what is going on? This should be positive, so I did make a mistake there. Make sure I'm still recording. I don't want to do this a 4th time. So this should be pretty flattened out, and then finally a little bit more. So there you go. So something like that. You should end up with something like that. Once again, there is a margin of error for this, but as long as they compare appropriately, you should be fine. All right. So that's how you do a slope field. So you literally just plug in the appropriate x and y values into the equation, and then you just draw these mini lines for each of these. Now, part B. Part B asks you to sketch a possible solution curve using this slope field through 0, 1. So I'm actually going to go back to part A only because I don't want to draw these slopes again. So we're asked to draw a graph. So how are we going to draw this graph? So first it tells us that the graph has to go through, 0, 1. So we have that. Now it also tells us that it has to be a solution to this differential equation. So what does that mean? It means it has to follow the slopes on this slope field. So for example, the way I draw this graph, the behavior of this graph has to follow the behavior of these slopes at these points. So the first one it tells us is that it crosses 0, 1. Well, 0, 1, the slope is 0, right? It's a flat horizontal line. Well, that means when I draw my graph, I should have, if you recall from back when we were doing mins and maxes, you should have something that looks like this. Okay, you should have a graph that looks like this. Okay, so remember, if you recall, one situation in which you would have a flat horizontal line as your slope is when you reach like the peak of a hill or the peak of a mountain, which is what you would have here. Now, another question might be, why'd you draw it curving downwards? Why'd you draw it curving downwards? Now, the reason why I drew it curving downwards is, if you notice, this is what I was looking at. If you notice, to the left of 0, 1, this line is going down and to the left. So this is telling me the slope should look something like that to the left of 0, 1. So that's why you got to make sure your curve matches that, right? If this is telling us that the tangent line is going down and to the left, that means this curve should be going down and to the left. Subsequently, on the other side, this slope or this tangent line is telling me to go down and to the right, so this curve should also go down and to the right, okay? And for the most part, it should follow in terms of steepness. It should follow what this is saying. So if this is saying this is how steep it should be, that is how steep your curve should be, at least in this approximate region. So if we were to continue on, right, so it would continue curving, and then it would probably do something like that. Continue curving. So you might be wondering, well, why did you draw the graph where it's starting to become more and more steep the more I go to the left and right? Well, if you look at the slope field again, if you notice, I'm just looking at this line right here. If you look at this line right here, so it's flat. Then it becomes a little bit more steeper. Then the more right we go, if you notice, the tangent lines become more and more steeper. So this is telling me right here, I'm looking right here, that the more to the right I go, this curve should become more and more steeper. And the same thing applies to the left side, right? It's flat, then it's a little bit steep, then it's more steeper. So this curve should follow that same pattern. Flat, a little bit steep, a little bit more steeper the more to the left. So you want to look at all parts of this slope field to make sure it matches up with the behavior of all those mini lines that you drew. So that would be an example of that. Now, once again, this is not going to be an exact science. Your curve, it would be perfectly acceptable if your curve was a little bit more narrower. You'll see that mine's a little bit more wider. If it was a little bit more narrower, you would probably still get full credit. I would still give you full credit. I'm pretty sure the AP graders would as well. You just got to make sure, once again, you got to make sure you follow the behavior that these slopes are telling you to follow, right? It should be flat here, then it should go down and to the left, down and to the right, more steeper the further to the left and right you go. Okay? All right, finally, C is a very popular type of question. I like to think it's a near guarantee you'll see a problem like this. So part B and C are similar. Part B asks you to draw a solution curve. Part C actually tells you to find that solution. So part C is basically telling you to find the equation. Oh, okay, good. Still recording. Find the equation of the graph that you just drew in part B. So part B was that green curve. It's basically asking you to find the equation of that solution curve that you drew. So let's do that. So the method that we're going to go over today, we're going to do a basic dry run of how you would do a problem like this. In these coming days, we'll do more and more problems akin to this type. So don't freak out. You will get more exposure to it. So the strategy that you use to find the solution to a differential equation is called separation of variables, if you want to look that up. Separation of variables. So it literally entails separating the variables on each side of the equation. So we have dy over dx is equal to negative x over 2y. So we're going to separate the x and y. So I'm going to do that by multiplying both sides by 2y. I'm going to multiply both sides by 2y. And that cancels out the 2y on the right side. So on the left side, we have 2y. dy over dx is equal to negative x. Now we're going to get that dx to the other side by multiplying both sides by dx. We multiply both sides by dx. So 2y dy, dx is canceled out, negative x dx. Now, so going back to what our goal is, we have the differential equation. We're trying to find what equation would give us this differential equation. So think of it this way. We have the derivative already. We're trying to find the original equation that would give us this derivative. So if you think just for a few seconds, I'm just going to pause here for a second. If you just think for a few seconds. So remember, we have the derivative equation. We're trying to find the original equation. We did that a lot in the last unit. Hopefully you thought about the antiderivative. That's what we're trying to do. We're going to take the antiderivative of this to find that original equation. And how did we do antiderivatives last unit? We took the integral. Now in this case, we're going to do the integral both sides. Because think of the integral as just like adding or subtracting in terms of it's just an operation. So if I do the integral of one side, I have to do the integral of the other side. So if we do the integral of both sides, we end up with y squared is equal to negative x squared over 2 plus c. Now, first comment. How do we get these antiderivatives? Well, at this point, we're just doing the reverse power rule. So 2y becomes y squared because we add 1 to the exponent, so it becomes 2. And then we divide by 2, so the 2's just cancel out, so it's just y squared. And then negative x, same thing, add 1 to the exponent, so it becomes squared. And then we divide by the exponent, which is 2, so negative x squared over 2. Now, you might be wondering, why did I write plus c only on one side, even though we found the antiderivative on both sides? Now, the reason we did is because eventually this answer will only have one constant. Now, you can put plus c on both sides, but eventually we're going to combine those plus c's into a single constant. So it's more convenient to just write a plus c on one side. Now, we're going to find this plus c by using that point. So we're told the point 0, 1. Remember, which just means x is equal to 0, y is equal to 1. So when y is equal to 1, so 1 squared, x is equal to 0, x is equal to 0, so negative 0 squared over 2 plus c. So when 1 is equal to y, 0 is equal to x. So I just plug that in. So 1 is equal to 0 plus c, so c is equal to 1. So that's how you solve for c. So that's what we did. We solved for c. So now I just put it back in. So y squared is equal to negative x squared over 2 plus 1. So this would be your answer. Now, depending on the problem, you might have to change it up. I would personally write it like this. I would write it as y squared plus x squared over 2 equals 1. There isn't any reason why. I just preferred variables to be on one side. Now, you might have a question that asks you, including on the AP exam, where they tell you find the solution as y equals. Okay, so that means you have to get your final answer as with y by itself. So in this case, all you would have to do is just take the square root of both sides, and that would be your answer. So you just take the square root of both sides, and that would be your answer to get the y by itself. Because since y squared, square root, cancel it out. So once again, that was a dry run of a problem we'll see a lot more of in the future, this idea of finding the solution to a differential equation. Once again, this method that we used was called separation of variables. We'll see it a lot more of in the future. Otherwise, I hope you guys are doing okay. I hope nobody's getting sick. And I hope you enjoy the rest of your day. Please let me know if you have any questions, comments, YouTube, Google Classroom, email. Always feel free, people. I think I've done a relatively good job up to this point responding to emails, responding to comments so far. I hope this lesson went well, and I will be seeing you guys in these next few days.